Multivariate time series are prevalent in emergency management where each time series may correspond to a number of customers losing power throughout the hurricane time at a particular county. On the other hand, in public health domain, a time series may correspond to a number of infected cases in a region during an epidemic. In a similar way, such kind of a set of time series may represent for all the domains and also can be prevalent in various other urban scenarios. So a segmentation on such multivariate time series data, they may correspond to an set of events. So an urban domain experts, they may want to use multiple segmentation algorithms to identify such set of meaningful events based on the domain and the data. Now, each figure show that the segmentation algorithms we use are different. It's because for each of these data for hurricane power failures, the segmentation algorithm we used, they can get the type of event which is very different from the segmentation algorithm we use in the historical diphtheria cases or in public health domain. Similarly, another different segmentation algorithm we had to use for serious influenza cases. So for each event, domain experts want to identify the time series of interest or TOIs which can give them actionable guidance such as resource allocation. However, the existing segmentation algorithms do not provide such TOIs. We define time series of interest as actionable guidance for the domain experts. Another way, the actionable signals which are more susceptible for a particular event. Now, for an example, in hurricane power failure, actionable TOIs are the regions where domain experts need to send resources quickly. Consider figure A, where each time series represents the number of power outages during a hurricane in a county. Segmentation is given in terms of beginning of the hurricane, when time series face severe damage, and end time of the hurricane. In figure B, for the event at C2, the time series in green box can be easily visible from figure A, but the ones at brown box cannot be observed easily. But these time series are also important to capture as they are happening due to a separate tropical storm far away from the hurricane trajectory. Such time series are also not be easily visible using an intensity plot as well. But all these time series in green and brown are also actionable as domain experts need to send resources to these regions to quickly fix from a damage. So the existing interpretable model behavior algorithms, which generally help understand the model behavior instead getting actionable insights for a segmentation. This time series may or may not also not give actionable directives, even if we can get the time series in terms of with interpreting model behavior. Also, the experts need to understand the model intricacies for each different segmentation algorithms, which is too technical, and also they can vary among different segmentation algorithms. One of the such state of the arts use HMM, that hidden Markov model, to provide segmentation. On the other hand, other types of state of the art segmentation, they actually use an optimization to learn the underlying correlation network among the time series and eventually use that network to provide segmentation. Hence, both of them are too technical and domain experts need additional technical help. So, to solve such kind of a problem, we introduce a novel problem rationalization for time series segmentation, or in other way, RATS, in terms of constituent time series. Rationalizations are the time series which can provide actionable guidance to domain expert for their interest. We provide rationalization when segmentation is a black box and we want to generalize this problem to work for any multivariate time series data. So, for each event in the segmentation, we represent rationalization, which are basically a weight vector to provide importance weight of each time series for the corresponding cut point. or an event. Our challenges are: first, we do not know anything about the time series data or the segmentation algorithm. Next, we want to map constituent time series to actionable directives, as we show in the hurricane power failure data. This figure is showing an overview of our big picture approach, where we want to view our input, time series, and segmentation as a graph network, and our goal is basically to solve using such network to solve a graph optimization problem to eventually get rationalization. So overall goal our optimization will be to motivate the rationalization in a way that we want to hypothesize that our black box output or given segmentation is best than any other possible segmentation that can be found on this data. And we want to get rationalizations as which can learn weights for each time series, which eventually can make this given segmentation as the best. So in our idea to map such input to a directed weighted graph is to use a segment graph data structure where each node consists of set of possible segments in S, X. Example, if there are 1 to t time points, t1 to 2 can be one type of a segment represented as S12. Similarly, S13 can be a segment represented from t1 to t3. Similarly, we can get segments like t1 to t4, t1 to t, etc. and t2 to t3 this way. So there can be t square such possible segments or nodes in the graph. So for the edges in the network consists of all possible adjacent segments. Example, S12 is since S12 and S23 are adjacent segments, that is time point T2 is a event between them. So there can be an edge that is E123. Similarly, 23 and S234 is an adjacent segment, so there can be an edge 234. On the other hand, 13 and 24 are not adjacent, so there cannot be any edge between them. So another way, each edge also has an associated edge weight to represent the edge cost based on the changes of the time series across the edge. Now we can map the black box segmentation as a graph path, where as an example, if the segmentation consists of two cut points such as at T3 and T5, we can call the path in terms of S0 to S13 to S35 to TA, where S0 and TA are two dummy nodes to represent start and end of the path. So next, how can we represent each edge weight? We can represent in terms of a vector which eventually gives changes of subsequence of each time series before and after an event with respect to some statistical time series features and distributional moments. Now, to map the problem rationalization as a graph problem, our optimization is to learn rationalization weight which can make graph path PB as the best path than any other paths in G. And however, to the number of edges since the number of edges in graph is cubic, if we want to learn rationalization for each edges separately, this will increase the complexity of the optimization. So our idea is to instead learn a latent vector alpha which can be applied for all edges and use alpha with our defined edge weights that can now, so rationalizations will be presented in some function of h of alpha and corresponding edge weight. Some research challenges are to develop graph optimization how can we define such a best path? That means we need some kind of a metric to define best path. We view this metric as a longest weighted path. Next, what function we need to combine alpha and edge weights to generate rationalization? Since our rationalization is in terms of constituent edge weights, we use dot product of two vectors since alpha and edge weights both are two vectors. And we want to get time series importance weight in terms of both alpha and edge weight. Next, how can we define an objective of alpha for the optimization, which can eventually make PB as the best path than any other paths in G? Our goal for the optimization hence to learn alpha, which can maximize the difference between two paths, that is path our given segmentation path PB and all other paths with respect to all other paths in G. So delta pi can represent such path where PB is our length of our path given which is we found by given segmentation, and pi rest consists of the sum of all other paths in G. And since k is a total path, since we want to sum all the optimizations, so it will come that total that pi b needs to be used k minus 1 times. So next, our this is our formal problem where we map the actual original rats problem to a graph problem. And our idea is we map input data and the segmentation to a segment graph, and the idea is to learn alpha using the optimization and then generate rationalization for each event in the segmentation. So for the optimization we also use two more constraints to have alpha sparse and bounded. To compute the difference of the path length for the optimization, first we need two different computation. One is path length PB, which is trivial, and another is computing all other paths in the graph, which is non-trivial. Since the number of paths in graph is exponential, so if we compute each path length separately, it will take exponential time. Hence, for an efficient computation, we propose a lemma which can solve such problem in OT cube solution. And the idea of the lemma is to calculate basically how many paths they use the corresponding edge in the graph. So we only need to go over each edge only once to calculate the path length computation. In other way, in total, it will take OT cube for all the edges. You can see the detailed proof in the paper. For evaluating performance of our rationalization, we choose the popular and publicly available multivariate time series data. For each data, we use rationalization as based on how the data is defined. For an example, in motion capture data like chicken dance, the sensors represent each different each different sensor represent how they are captured the motion, and which mainly change based on the each different labeled motion. And so the rationalizations are based on the sensors which mainly changed due to the change of the motion. Similarly, in a great Barbet kind of data where the voice recordings are basically the data sets, so the rationalizations are based on the birds whose voice recording starts or ended at an event. Now, for baselines, we consider models based on the intuition to check performance against models which do not principally consider any optimization, and also we want to check how each cut point, considering each cut point independent of the overall segmentation works. So first model is feature based, where we used edge weights for our segment graph, and we select the time series which has high value in edge weight. Next, magnitude based, we select time series with high change of intensity or values across an event. In forecast error based, for each segment has been trained using an LSTM, where we train each time series for each segment, and we want to forecast the time series values after that particular segment, and we want to select the one which has high forecast error. For example, we trained the model based on green, each separately for the green time series and red time series before C1, and we want to forecast the time series values after C1 and and the one which has highest forecast value came up as rationalization. Our algorithm outperforms all other baselines to find actionable time series of interest. This can show eventually from the table that statistical feature analysis, change of intensity, or forecast model, none of them can give actionable time series of interest for a black box model. So, to capture rationalizations, we also observe that considering overall segmentation is important rather considering independent events. Hence, learning of alpha is also useful. This is actually a case study based on the number of power failures that happened during Hurricane Harvey in the hurricane affected counties at Texas, where the black box segmentation has been found based on a state of the art segmentation algorithm. So, for an event correspond to C3, if we see that when the hurricane is actually ending, the power failures are decreasing, but at the same time our rationalization captured the time series where on the counties where power failures are also increasing. So we found that this is happening due to a rising water of Nations River which closed down major pump stations. This is another case study of COVID-19 interventions where we want to show our rationalizations are meaningful and actionable for domain experts. Each time series in the figure consists of the number of COVID cases in a US state from January 1 to May 2019. For segmentation, we collect state of emergency declaration dates of some states. Note that it is only for few states, not all states. Each cut point in the segmentation is basically the date after 2 weeks of emergency declaration, as we view incubation period of COVID effects are 2 weeks. For example, C1 is 2 weeks after state emergency declared in California. As there is no such centralized database to collect all types of NPI interventions, such as restaurant or school closures, our goal is to check whether rationalization can guide for such NPI from a partial set of segmentation. C for cut point C1, our rational, which is based on a state emergency of California, we found our rationalizations. They also find the states which had NPI interventions, other NPI interventions. That is, Massachusetts and Louisiana had school closures. Connecticut has restaurant closure. Hence, for the overall segmentation, our algorithm captures 60% states which had NPI interventions exactly 2 weeks before, and 87% states had interventions less than 3 weeks. Such indirect methods can guide epidemiologists enable their disease forecasting model, where using interventions is crucial for modeling disease spread. One more case study is we found on historical diphtheria case, where we collect time series as yearly case of diphtheria and TB in all US states from 1900 to 1950. We use the same segmentation algorithm for both the data, and hence we see we get similar segmentation. For diphtheria, the events correspond to the campaign start time, outbreak in Chicago, and vaccine interventions. However, now if we see this figure, the middle and the bottom figure is showing the rationalizations for diphtheria and TB. And we see that our rationalizations capture positively correlated weights for all the states, especially Chicago where the outbreak had happened. Now our report suggests that this type of an association or positive correlated weight they may happen between diphtheria and TB due to a presence of an iron repressor gene. So to summarize, our overall contributions are: we introduce a novel problem to identify actionable time series of interest for urban domain expert. We propose an algorithm to solve such problem through graph optimization. We show our rationalizations can successfully capture time series of interest in different domains such as disaster power failures and historical disease infections. Such problem can also help in ongoing disaster if the segmentation is provided in real time. Some reference of the popular segmentation algorithm we use in our paper, and you can find our dataset and codes as available in the given link. Thank you.